Okay, it's time for post-Malthusian industrial growth. So we're getting towards the heart of the course, and I'm looking behind me on my camera and I gotta clean the board. Okay, so post-Malthusian industrial growth. We're getting towards the heart of the course, understanding the process of economic growth. Then, of course, we're going to link it to all sorts of other interesting phenomena like use of non-renewable natural resources and pollution emissions, etc. Okay, but first of all, growth itself. Oops, got to check, sort my technology out here. There we are. Okay, slide 2, the Solow and Ramsey models. So we're going to spend a lot of time on the Solow model and a little bit of time on the Ramsey model. And of course, I'm sure you've all seen the Solow model before, but you're going to learn some new stuff today. I'm pretty confident, all of you. Even when I've taught this similar stuff at PhD level, gone through it very quickly, but still people are like, oh, okay, wow, that's interesting. So, slide 4. Compare the following equations. Discuss similarities and differences. So, I'm going to take you through this. You might want to pause your video here and think about this. Okay. Okay. So, what are the similarities and differences here? We've got a chemical equation. We've got iron ore and carbon turning into pure iron and carbon dioxide in a chemical equation. We've got a thermodynamic equation. Oh God, how do we read that? It's the change in the Gibbs free energy is equal to the change in enthalpy minus the temperature times the change in entropy, right? I think. It's too long ago. It's all chemistry. My undergrad's in chemistry. I think I've probably said that before. And then what have we got? We've got yi is equal to the minimum of ALLI, AKK, KI, and ARRI. So what are these equations? So, let's leave the middle one because that's sort of tricky. What's the first one? It's saying if you take 2 moles or molecules or whatever of iron ore and 3 moles of carbon, and somehow if you stick them together and say the magic words, you can end up with 4 moles of iron and 3 moles of carbon dioxide. And there's a balance here on each side of the equation, isn't there? That the number of moles of iron atoms, oxygen atoms and carbon atoms are the same on each side. That's why we call it an equation, because we're equating 2 things. There's also a hell of a lot that's not being said in this equation, right? Like, how did this actually happen? Will it always happen? Do you just have to mix them together, or could it go the other direction? Okay, it's a simplified, there's so much not there. Okay. Now, let's look at the last one. So I said for any equation it has to be that the stuff on the left side is equal to the stuff on the right side. That is the equation, isn't it? Which means that the units have to be the same, like moles. So we've got like 4 moles of iron, 6 moles of oxygen and 3 moles of carbon is equal to 4 moles of iron, 6 moles of oxygen, 3 moles of carbon. Somehow that's the top one. But what are the units of the bottom equation? How could the units of that lot all be the same? Well, let's have a look at this bottom equation. What's this actually saying? yi is equal to the minimum of, oh, I just had ordinary brackets, it doesn't matter. ALLI, AKKI, and AR, RI. I don't know if you know what this production function is called. This is a production function, that's the first thing. Okay, it's saying if we stick in these inputs, Li, Ki, and Ri, and with these technologies, or with this technology implying these productivities, Al, Ak, and Ar, we get this amount of output, Yi. It's a production function. Okay. And what's this all about? What kind of production function is it? Anyone know? It's Leontief, right? This is Leontief. I'm going to have to do something about this pen for the next video. I hope this is still visible for now. Yeah. I've got a super environmentally friendly refill for this pen. Okay. It's Leontief. So what does that mean? What does this mean? It means that the amount of product we get is equal to the least of these three quantities. It's like, how many pairs of shoes do I have if I've got 7 left shoes and 10 right shoes? It's the least of those two, it's 7 pairs of shoes. Okay, so there's no substitutability between the inputs. That's what this is saying. The amount of product you get is the least of these three. Now, what about units? What could the units of this be? Well, let's give our product some generic name like a widget. Then Yi could be widgets per year. Okay, that's the flow of production. But then, what's Li? Well, Li could be workers, right? But then what's Al? Al is the productivity of workers in producing widgets. So that must have units. Widgets per worker year. Yep. Widgets per worker per year, that's productivity, isn't it, of workers in making widgets. But then when we look at this, we've got widgets, workers, year. That turns out the units of this term are widgets per year, which is just as well, because these commas, given the way this looks, each of these must have the same units as this. Which wouldn't be the case if they were like multiplied by each other, but given this production function. K is capital, isn't it? So, what are the units of capital? So it depends, actually, the units of capital can be different things, but the classic definition of capital is just foregone consumption. So we could even measure capital in terms of the widgets. It's how many widgets we've kept behind in the production process. So Ki could actually have units of widgets. It's the stock of widgets in the factories that we use to make more widgets. And then what's Ak is the productivity of capital, which is widgets produced per widget of capital per year. And again, those go out and we end up with widgets per year. And this one, Ri, is like some resource input. It's tons per year, isn't it? The flow of resource input in tons per year, and AR would be widgets per ton. Yeah, how efficiently can we turn a ton of natural resource into a widget? It's widgets per ton. The flow of resources, inputs, is tons per year, and again, we have widgets per year. Okay, so it's really good exercise to think carefully about units. Okay, what drives, slide 5, what drives growth in Y? And what drives growth in Y over L? So, oh, sorry. I was about to pause. Slide 5, we've got a bunch of different equations here. Y equals ALL, y is a function of ALL, AKK, and y is a function of ALL, AKK, and ARR. So in the first one we have only one input, labour. In the second one we have labour and capital, which is the standard. In the third one we put in resources as well. I've talked you through units already. I kind of got ahead of myself. I've talked you through units. Here, what drives growth in Y? Typically in a real economy, it's, well, let me create some space for myself here. So if we take this Y equals ALL, well, we could either raise AL or we could raise L. If we raise L, yeah, we can produce more stuff because we've got more workers. But, sorry, that should be capital Y. But that's maybe not that interesting because what we really want to do is raise production per person, and that's just equal to AL, isn't it? So to raise production per person, we need to raise AL. More generally then, if Y is a function of ALL and AKK, potentially we could raise capital. We could save up stuff we've produced to raise capital and then produce more. So we sacrifice consumption today to consume more tomorrow. But what Solo showed was that will only help you to a certain extent. After a while, you'll suffer from diminishing returns, right? Because piling up more and more capital isn't going to give you more and more production in the long run. And if we throw in resources as well, then again you could say, oh, we can use more and more resources to grow more and more. But well, where are these going to come from? We need labour to get these out of the ground. So if we shift labour from here to here, that, there's going to be an optimal way of distributing labour, and then you're not going to get any more growth by trying to use more resources. You'll lose production. To grow, you need to raise these. Yeah. To get sustainable growth, you need growth in productivity. And since the main input is labour, you need growth in labour productivity. But once resources get scarce, you need this to grow as well. Okay. I should say one more thing about comparing the compare and contrast thing with the different equations. I said the chemical equation, it focuses on one aspect, the balance between the quantities of the different chemical elements. A production function also focuses on one aspect of the production process. It focuses on particular inputs and the output. And you could argue, well look, if we had this production function, for instance, then you could argue, well, this is incomplete because there's no natural resources. And therefore, some people have argued, therefore this makes no sense. Okay, that's a bullshit argument, not to put too fine a point on it. Because this is a model, okay? All models are simplifications of the true production process. You could always say there's things missing from the production function. Oh, the workers, they need air to breathe, otherwise they can't work, therefore the air should be in the production function. No. Okay, it's a model. It's a simplification. Okay, that doesn't make it wrong. It's a simplification. It helps us to understand things. Of course, if we're interested in natural resources, pollution and environment, we should add something like this to our production function. That makes it more suitable to address those questions. Okay. I think that's it for now. and I've already gone on for 15 minutes. So yeah, I think I can't believe how long I talked on this. Sorry if you got bored. I'm going to stop this video now, and I'm going to start a new one for slide 7, neoclassical growth models.